Interesting. Who else is in the call?
Yeah, so probably there's an issue with YouTube Live. Let me quickly
Take your time.
fix it.
You have more time. Whoever is listening and I'm unable to speak, just drop your questions in the chat. I will answer them.
Yeah, so probably there's an issue with YouTube Live. Let me perform some quickly sound
Take your
test.
time.
Fix it.
You have more time. Whoever is listening and I'm unable to speak, just drop your questions in the chat. I will answer them.
Yeah, you are audible.
Right.
Yeah, so
XSpace is a little bit
probably there's an issue with YouTube Live.
So again, like we are waiting for 3 more minutes. We are like going through some checks for YouTube. After that, we will start. So like anyone from audience who want to interact
can request to speak. I will allow them to speak.
I'm unable to. And if you're not able to speak, just drop your questions. I see a few hands.
May I ask the question?
Yeah, go ahead.
Okay. Hello, Bhaiya. My name is Rishabh. My question is regarding the Saturn V series. Since the topic is Saturn V series of rocket.
Saturn V series, okay.
Right. Since it was discontinued after the launch of Skylab.
Okay.
Right. I just want to know, the topic is a bit different from what it is designated. But my question is regarding the N1 engine, the engine that was used in the Saturn. Why was it so unstable? And why we human are still not able to have more powerful engine than that of Saturn V? So if you can answer it.
Sorry, Rishabh, I don't really follow the rocket engine. I'm not, let's say, I don't have much of information there. Probably Titanium is also here. He could probably answer it. I followed Saturn, at least rockets as such.
Okay, so like we are live on YouTube and all tests are successfully performed. So I guess let's start. So, ladies and gentlemen, esteemed guests and fellow space enthusiasts, welcome to XSpace, where we embark on a journey beyond the confines of our planet and explore the wonders of space exploration. Today, we gather to delve into the realm of lunar exploration, a realm not just for professional astronomers, but for enthusiasts, hobbyists, students, and basically for all. Like, as our speaker said, like he want to make this X space for like normal janta. So you may enjoy a nice blend of technical details and some good maybe animations. So like if you want to see simulations, we are having on like our YouTube channel. So all credits of that animation goes to Chandra. So okay, let's start. So let's start with our like first maybe topic. So tell us, Chandra, like enlighten us how we can pursue like lunar exploration as a non-professional enthusiast or hobbyist.
Like, yeah, hi.
Like imagine I don't have much knowledge about softwares. So like I request you to please mention what are all the software that you use.
Yeah, definitely. So as I said, the topic is more or less separated into two major chunks, right? One is the first one is about the lunar exploration in general. For everyone, I'm Chandra. You don't need to work for a space agency or private industry to discover something or to explore around. So it's going to be around that topic, and the second part is going to be more or less on the simulation stuff that I did. That's in the YouTube, or you can also find it in my Twitter handle. So, but I want to start by saying few disclaimer just to set a base. I started working on it some time ago, and I'm not expert in this. I'm not a planetary scientist. I do everything as a in my non-professional capacity. So you could probably draw parallels to me as an independent researcher, right? And today's topic is I'm not gonna talk more into details, but of course, feel free to reach me out for a larger discussion. I'll try to keep this topic very simple. Try to avoid a lot of technical details, so it's appealing to larger audience, I guess. And I might say something incorrect or might not explain something clear. Please, at the end of the talk, you have the session, so please feel free to correct me. I'm always eager to learn more. So let's talk about the lunar exploration in general, right? So why is this interesting, or why are there a lot of missions going to the South Pole region, for example? Or why is there suddenly a lot of interest in the past years? Why are there lunar landers going around there? Why are the communication satellites going to moon? And there are a lot of things are going around. It's a lot more hot, this space. So you could draw parallels to like another moon race, right? We had one early, and then now you have another kind of a race, right? So the idea is that there is a possibility of finding water ice there and a lot of other minerals in the PSR region. So this is so-called permanently shadowed region. So what does it mean? It means that there are parts of the south polar region of Moon that are permanently shadowed. That means light doesn't reach there because it's so at the bottom, and then sun doesn't reach there a lot. There's not much of sunlight there. So very less chance of heat there. So the idea is that there would be water ice there because it's too dark, so there might be chances of water there. You can also say that this is also a place where the next frontier would be for humankind. There would be human explorations there, and they will use Moon as a gateway to reach to other places like Mars. You know, Elon Musk has already said it. So Moon is used as a gateway to reach to the other exoplanets or planets around our solar system in the near future. So this is why the whole lunar exploration is in hype. But as a non-professional, like Amjanta, like us, you or me, why is this interesting for us? Like, what makes it more interesting? Traditionally, you know that this is only for space agencies. No, only those people work on it. But in the past months, in the past years, this has been more accessible to the wider community. Because of the rise of social media, you see a lot of people posting it, and that's why it's more like appealing to everyone. And you could say this is like democratizing the exploration of space. So this is why it's a little bit more appealing to us. But not a lot of people know what's out there, right? So when I started exploring, I did not know what's possible, what kind of instruments are out there, and how I can access them. This is not really known, right? So there are currently 3 main orbiters around Moon, which are active, where you could download the data and look at the data. And there are several instruments, several cameras, let's say, and they are in the visible spectrum. So you can take images, you can look at those images, right? So the most popular one that you all know, or everyone knows, is a Lunar Reconnaissance Orbiter, LRO. So NAC and WAC. Most of the images that you see from NASA or any other space agencies are based on these instruments. So they have been there forever, since 2009, and they have taken pretty much all parts of Moon. So they mapped up the entire Moon, and everything that you see is based on the LRO mission. The resolution is about 0.5 to 1 meter per pixel, so it is high resolution, but not high enough. Another one, is our beloved Chandrayaan-2 orbiter. It's launched in 2019, if anyone doesn't know it yet. And it's got two instruments, OHRC, high resolution camera, and another is a low resolution camera, which is called a TMC2 camera. High resolution camera is about 30 centimeters per pixel, so very, very high resolution. The other one is 5 meter per pixel, which is the TMC2 camera. I'll talk about that later. And the other one, which is also not well known, is the one from Korea. It's called as KPLO, Danuri, in short. They also have instrument, but this instrument belongs to NASA, but the orbiter itself is from Korea. It's launched in 2022. And so this is very interesting instrument. It's called a shadow cam. The resolution is about 1.7 meter per pixel, so in the medium range, so between Chandrayaan-2 and LRO. But one special thing about shadow cam is it is specifically designed to watch the PSR region. So it doesn't have too much of resolution comparatively to OHRC, but it is tuned in a way that it can take really, really good images of the shadow region. So there is a high signal to noise ratio. It's about 100 over the PSR region. There's a lot more details into it in the ShadowCam paper. I can share it to anyone who's interested. There are other two also. One is from Changi, and the other one is from Changi is from CNSA, China, and the other one is from JAXA, Kaguya. Both are now not active, but the data is out there. Right. So these are, in a way, these are all the instruments that are out there today, right? So, and the data of all of these instruments are released by those respective agencies, but it's available to everyone, but there's always a catch. So there is this thing called as a lock-in period. So let's say you're seeing it, right? NASA has released a picture of SLIM recently when it landed. You might want to look at the actual data of it, but you can't because of this lock-in period. So a lock-in period is a period that any or most agencies have until they release the data to public. For example, the NASA LRO has 3 months of lock-in period. What does that mean? It means whenever they take a picture of anything, they will wait for 3 months until they release it to public. And you also have that for ISRO, 6 months. So the idea is that since I've talked to folks who are working there, they've told me that this specific lock-in period helps the scientists, the principal investigators, and the other team members to exclusively study on it because they have the one who were there since the beginning, sending out the instrument out there. So they get the first dig at this instrument, so to speak. So that's why they get the first data so they can work on it, and then they will release it to public. So we have seen it right for Chandrayaan-3 data has been released by, Chandrayaan-2 taking a picture of Chandrayaan-3. This is the data from OHRC released recently by ISRO. So we are going to expect also another release sometime soon. But anyways, so these are, so data is out there. But so you might ask, how do I download it, or what kind of format is it? Can I look at it? So normally these are distributed in the so-called exchange formats, and the exchange formats are different for different purposes. But mostly there is something called as a TIFF file, which is a direct image data, like JPEG file, your PNG. There's also TIFF. TIFF is also like a normal image data. You could open it in any image editor and then take a look at it. For example, all the data like SLIM is like SLIM data by LRO. If you go to their blog and click on the images section, there are a bunch of images that are released by LRO. Right, on all these images are downloaded. You could download them in TIFF files. You can directly open them in your editor and then look at it. Any image editor would be fine. So TIFF is you can use any kind of open source, closed source editor to open this. There's also a special format of TIFF, which is called as a GeoTIFF. It is a little bit special because it also contains the location information as well. It's called as a GeoTIFF, but it looks like a TIFF, but there's the data embedded in the image itself. And you could view it with any editor, like any picture editor that you could use it. But you could also open the image data and then look at if you look at, I don't know, a crater in an image and you want to know where it is. This is the image, this is the location data. And GeoTIFFs are also, you could also use any kind of open source tooling like QGIS. It is if you go to Google and search for QGIS and search for it, there is an open source tool. Just download it, and you can open anything that I talk about in this talk in that software. You don't need to know a lot of details. You don't need to learn about it. Just take the image and then dump it in the editor. You are able to view those really huge files. And I'm talking about gigabytes of a single file. So you could open it, start playing around. Everything that is possible with the TIFF file. Another most popular one is a so-called PDS format. This is a planetary data system format. This is a super flexible format, also done by NASA. Super flexible format. So what is so different about this format is that it is very, very flexible. That means that you could store anything in this format, like instrument data, where it took the image, where it was in terms of location, and where was the sun when you took the picture, and what is the orientation of it, the instrument, and so on and so forth. There's a lot of data. Right? Everything is possible with this PDS format. So this is the most common format out there. And almost all the space agencies have this format. They share the data in this format. ISRO shares the data in PDS version 4. I don't know if everyone or some of you have listened to the talk by our chairman. He mentioned that all the data of Chandrayaan 2 and Chandrayaan 3 is globally available. Everyone can use it. All the researchers across the globe are able to view this. And we have a standard format. I think he mentioned it a couple of times. And this is the format. PDS is the format, and version 4 is the latest version out there. And we use that version. ISRO uses PDS4 format to distribute the data. It's a very standard format, up to the mark. And there's also version 3 as well. Some space agencies use it. But in general, NASA, JAXA, CNES, also JAXA, almost everyone shares the data in PDS format. So if you want to know anything about it, this is the format, and QGIS, you are able to view this with QGIS. There's also another one which is very, very special to NASA itself, and it's called as a ISIS, and the format is called as a CUB or CUBE. It's a CUBE format. I think I've talked about it in my post some time ago, comparing with the TIFF file. I think I might have ranted a little bit. So CUB is also a very special format by NASA. It's very interesting format. So the idea is that CUB is a CUBE file is a very, very heavy file. What do I mean by that is you can store everything into it, like instrument data, position data, and also sun positions and almost everything into that format. The difference between PDS and then an ISIS CUB is, or CUBE file is, ISIS tooling from NASA is it gives you many toolings for it, many toolings with this CUBE file. So you could process a lot of data in it. You can say, if you want to find Chandrayaan, like you want to find it, right? And they say ISRO has shared the location, and you're curious, you want to know where it is, you want to watch it directly, right? So instead of finding, so you can open the editor that comes with ISIS. It's called as Quick View or QView. Open your file there and then search and put in lat and long, and then you can find it. It's exactly the same as Google Maps, right? So you have lat and longs there. Also, you could find lat and long, dump in the position information in this cube file, and then you can find it. So this is the most straightforward way. The other way is that you could also have more processing of the image. If it's too dark, you can brighten it up, take a look at it. If the crater is too dark, you can also brighten it, and then do a lot of image processing stuff. So it goes into image processing, and there's also a lot more information in there. You can use a lot of map projections and stuff, but it's in the more realm of GIS. But if someone is interested, you can ask me in the question. I can explain more about it. So very interesting format. So TIFF file, PDS, and ISIS are the three most shared format. TIFF is the most simplest one. ISIS cube file is the most, let's say, sophisticated format. So, and all of the files, TIFF, PDS, and ISIS, you could all use QGIS to open them. So you just need one software and nothing else. It's very, very powerful. Okay, so this is how you can download it, and these are the formats that you can use, but why would you want to do it, right? So the question is that why would you want to look into it in general? A lot of people have asked me, also my family has asked me, why am I doing this, right? So the low-hanging answer I would give is that it's got a lot of chances of learning, right? When you open an image and then look into Vikram lander all by yourself, find it and look at by yourself instead of looking at the picture shared by ISRO, it's a different feeling, right? And they're not sitting around and then sharing all the details that they find. They only share what's important for the mission, and then they get back to their own work. Share and then share what you find. So what I'm talking about is a possibility of discovering yourself. Very interesting thing. So it's not just craters and boulders. There are also different kinds of structures on Moon, which is very interesting and very spooky, even. So if you can start finding it by looking at the images. So it's a time pass, a lot of time pass. But you could do a lot of things by just looking at it. So for example, someone online, I think a lot of people have noticed, Shan also did this. He discovered debris of Chandrayaan-2 by looking at the data exactly like this. And we can also find interesting things about it, right? So, and the other thing is that you can also do a little bit of research about it and then learn about it. And that's why it makes it a little bit interesting to find it. So how can you download the data? There's also NASA website, NASA LRO. There's a LRO and WMS browser, and then you can find it. There's also a very famous LRO quick map, which is like a, let's say, Google map for Moon, in a way. You can, if you search for a location and you want to find any interesting location, you have lat-long position of the location, you can use LRO quick map. Search LRO quick map on Google and you would find it. There's only one, which is very interesting. And then dump your coordinates there, and then you can find your data there. And ISRO has its own website, ISRO Pradhan website. And you can you need to register to Pradhan and download the data there. There's, I think Chandrayaan-2 is there, and there are also other missions which are also there. But anyways, JAXA, CNES, ESA, they all have their own websites where you can register and download the data in the same format that I mentioned about, right? So this is more or less about it. And more or less, the other thing is that if this is not enough, then you can always have a possibility to make your own, which is what I did. I created this so-called SOMA portal to search everything, because I was not happy with what QuickMap was giving, and Pradhan was also not, it's very difficult to find things in Pradhan. So which is why I created a SOMA portal, and all my analysis and all my discoveries, let's say, quote unquote, are based on this. And that's why, that's why exploring it is also interesting. There's also one more thing I would like to say in this idea is that how did Chandrayaan-2 made a difference? So from my perspective, Chandrayaan-2 mission is a game changer for ISRO. I strongly I don't see this as a failure. I see this as it is kind of a success in a way that they have the kind of data that it gives us and the kind of exploration, kind of research data that it gave us, and I'm going to explain what I mean by that. But just to reiterate, there are two instruments, TMC2 and OHRC. Both are in the visible spectrum, so you have images out of it. So the idea is that OHRC has been quite instrumental in supporting the current missions and as well as the future missions. So what the scientists in SAC ISRO has done is by looking at the image data, because this is the OHRC data is pretty high resolution data, and they have designed some special algorithms to derive the elevation data out of the high resolution image data. And this is not possible with NASA. So NASA doesn't have, so the data released by NASA is there, it's widely available, but it is not really high resolution. So it's there, but it's not enough. And this is what the ISRO, what we did. This is why I believe OHRC is a game changing in this space. Because of the algorithms developed by SAC, they have derived elevation data out of the images. So what is elevation data? So this is just to understand the topography. So is it high, is it low, how flat is the area, and are there any boulders around where you land? And these kind of data in a very, very high resolution, you could analyze it. And this is not possible at all by LRO, not before Chandrayaan-2 at least. So for example, in Chandrayaan-3, this has been very, very helpful. I think I've written my analysis in my talk. We've done a lot of topography analysis there, and we found a suitable place where we could land on a flat area. This is how Chandrayaan-3 has, it helps in Chandrayaan-3. You can find my analysis there. So about SLIM, this is interesting. So in SLIM, they also used LRO data because that's what everyone starts to use. But the difference is LRO mission, the image data were used by SLIM, image data given by LRO is only, let's say, it gives you a general idea about the vicinity where you can land. But SLIM goal is to have a very, very precise landing, right? We have heard about this 100-meter landing, 100-meter precise landing. And this is not possible with the LRO because it's not high resolution enough. And that's where they use OHRC to pick a spot where they could land at a very, very high resolution. That's how it helped in SLIM. So what's going on with LUPEX and then other Artemis missions? And I also talked about this, right? So I've read a lot of research in this area, and what's going on with this is, so a lot of research is done by our ISRO scientists. So what they did is they identified a locations where the topography is really flat and there are not many boulders in it. And the same technique that the scientists in SAC have done, they use the same technique to find a very precise location where the area is flat, no boulders, and the rovers are able to navigate. Yet the landing area is rich of science data or collecting science data like minerals, water ice, and so on and so forth. This is not really possible with LRO. The images released by LRO. It's not precise enough, let's say. Anyways, okay, so with all this talk, what did I discover in the past months? Is that the obvious things is that you could see Apollo descender module, and of course Chandrayaan-3 Vikram lander. We have seen this already. I've shared this in my post. And the other thing is that the other two interesting things I found is the missing engine of SLIM. It hasn't been confirmed, but we will see. I shared my information to both JAXA and NASA. They're both evaluating it. I'm in touch with them. We will see if they will confirm it or not. And the other thing is that I've discovered a really large crater in the PSR region in the South Pole, which hasn't been cataloged by NASA because they can't see it because it's not bright enough for them. And we have a high resolution camera, so we can see it. So anyways, so this is a very high-level overview of the lunar exploration. I think that's the end of this topic. Should I continue?
Wow, it was like really interesting piece of information. Like I hope audience is inspired by this piece of information, and like we want you guys to try this out and like send your observations uh, for everyone. So, how did you like make such discoveries? Like, how? There are many people who are doing this. Like they are not professionals, but still do it. So, like, is there any way or like any method to do it, or like you just dive into some data and with some magnifying glass?
Well, in a way, this is like taking up. I mean, there are also scientific methods to find it, of course, because so the initial observation is that you find a possible location. There is actually for example, NASA has released a document where it has given such thing is missing. For example, the descender module has a flagpole, right? For example, it's also not there, but the location of that is given. So you just need to take a magnifying glass and then take a look at the image data. We just need to open the files in QGIS and start searching for it. That's like a brute forcing method. And once you find some, let's say, interesting objects, and then you could confirm it or confirm it based on the let's say the brightness values, for example. There are also other methods to do it, but this is the most easy, straightforward method, I would say. Open the image and then start looking for it. That's how I started it. But the more you do, the better you get at these things. But when you started, you just need to open it and then start looking around what you would find.
Wow, like that's really interesting. Like before moving to our like next topics on how do you make simulation kind of thing, I guess let's give audience a 5 minute break maybe. And so from audience, if you have any questions regarding this, like you can ask, and then like we will continue with our like next topic. You can like either speak on mic by requesting the access, or I can like you can simply comment it. Like either of way would be acceptable. Okay, so like today ISRO successfully launched Mark 2. So like big shout out to ISRO. We have got like okay, let's end the gang war and
big shout out to the
focus more on.
I don't know who of the audience is in the MK2 gang, but I think that settles the gang war in a way. Both are good.
Yeah. So I guess good to go for a okay. How much time does it take to find this kind of thing? And are you a fan of GSLV Mark II?
Yeah, I'm a fan of Mark II. Okay, despite what I say, I think it's a beautiful vehicle. I think it demonstrated its well, let's say its power today. I think it's one of our pride. I think this is it's what it is. I'm neither gang actually, despite what the sentiments are there. But neither gang. I love both. I love both Mach 2 and Mach 3. LLVM 3. I mean, right. What was the second question again?
How much time does it take to find this kind of thing?
How much time? Yeah, it depends on what you're searching. For example, let's say Chandrayaan 3 Vikram lander, right? It took me some time to find it. So what's a little bit tricky, which I have not talked because of the time constraint, is the data that they release in the equatorial region and in the polar region, right? So equatorial region, which is at the center part of the moon, which is it is very straightforward. You could find everything there, and very easy to open in QGIS and then take the data, dump it in QGIS, and then find it. So it doesn't, in terms of time, I can't really say. It can take days to months, weeks, I guess. I think in one of those talks, I think Shan has said that he took off and then he sat for days to find Chandrayaan 2 debris. So he's been working on it since, I don't know, some time now already. So it can take some time. So it's like finding needle in a haystack at the end of the day. Of course, it can take a little bit time. But the thing is, it also depends on what you are trying to search. For example, for Vikram lander, it took me half a day because I had to write special scripts to understand the data, and it took me a while to understand the data itself because it's on the polar region. Typically, polar region is a little bit more complicated to work with for me because the projections are different. Equatorial region is the best place. It's very easy to find anything there. So can take from hours to days to weeks. For me, SLIM, for example, I found the SLIM missing engine, which I say it's a missing engine, maybe not. It took me less than half an hour because I know exactly what I was searching, and I just wanted to compare the images, so didn't take me long to find it. Vikram 3 lander took me more than 2 days to find it because I didn't understand the data at all. It was very difficult for me to find it. Apollo 3 lander took me also. It was again like finding with the glasses because the location data shared by NASA is different to what you see in ISRO's data. There are location differences. Again, this is a little bit involved. So there are inherent location differences between different agencies, at least ISRO's with NASA's. So we just need to go around and then find it. It took me like maybe a day, I guess, to find the lander and so on and so forth. So it can vary, depend on what you're trying to search. Water ice is something that I'm looking right now. That will take a lot of time because you need to also look into you need to combine several information, pixel data, and you also look into the spectrum of it and so on and so forth. That will take more time. So it can vary. But good question.
Okay, so let's dive into the world of orbit simulation. Like, how did you create that propulsion module animation, like simulation, and like SLIM simulation, and like Apollo lander descent simulation?
Yes, right. So how do I make these trajectories and stuff? So this topic is a little bit more involved. I will try to simplify as much as possible. So, but a little bit, I will try to explain it with a short background information, right? So first you need to understand what a trajectory is, right? So you know that space objects or objects in the wide empty space are going around, and it's a three-dimensional space. So when I say, hey, the trajectory is not good, or it's flying around a planet or whatever object, what do you know about this trajectory? So let's understand this. So for example, I'm going to give an example, right? When everyone is little, I hope, they all played with this model rocket. Just took a piece of paper, folded it, and then tried to throw it inside the room, right? And then you try to guess it where it would land, for example, and you try to, I don't know, see where it would hit. If someone is on the other room, you try to go run around and then catch it. So you could draw parallels to it. But in reality, what you're trying to do is you're trying to throw a rocket in a room, this paper plane, and you close eyes and try to guess where it is, where it will land. So this is a parallel what you could draw to remember it. They're called as the so-called ephemeris. It's a special kind of data, for example, special kind of information, so to speak. And it's a little bit more involved about, I'm not going to talk about it in this session at least, but the idea is that there are the so-called ephemeris. These are special, let's say, time variant data, right? So there are a few data that changes over time. You would have seen it, right? If you take a graph of it, if you take a 2D graph, colleges and schools, you draw a line right there, and so the data changes over time. It's the same thing, same concept here. You have a time variant data, and these are special data which tells you some information about the spacecraft. And you could imagine this as like as a special table, right? In special table, you have this so-called data, and then the data changes over time. So what are these data? The most interesting part of this so-called ephemeris are the position, velocity, and attitude. So a position is where is the spacecraft at any time, and what kind of velocity does it have, and what kind of orientation that it has, right? In the both 3 dimension, because they are 3-dimensional species. It's in three dimension, X, Y, and Z. So the same thing is that when you throw a model rocket, you want to know where it is, like how high it is. You need to know, is it to your left, is it to your right, or is it to your front and to your forward? So these are the 3 dimensions that you want to know. But it's easy to know that there is a position of a spacecraft, right? But what is also interesting to know is that position according to what, who's observing this, and who's fixed it, who's looking at it. So this is also interesting, right? So for example, like you throw let's say this rocket into this in your room, and then there's someone is there next to you. Your friend is there, right? So your friend is also looking at you throwing the rocket, or throwing this piece of rocket, a plane, and then he's also watching it. So he also knows where it is, but that's according to him. And you're also throwing it, and you know the position according to you. So there's also this concept about who's observing it and who's fixed it. And there's also something called as inertial frames and stuff. There are also the concept is a little bit too detailed. We don't want to talk about it right now. So this is the idea. So there's also position, velocity, and attitude, orientation, and there's also references. So for example, if you want to know the position of a spacecraft, you want to know where is the spacecraft with reference to sun, right? So for example, how far is it from sun? So if you put sun at the center and you want to know where it is, you want to know how far it is in XYZ direction, right? And this is a so-called heliocentric system, like sun fixed reference system. For example, there are satellites that are going around the Earth, and you want to know where the satellite is in relation to Earth, right? And this is called as a geocentric system, which is relation to Earth. And there are also other systems which we don't care about right now, but these are the most common one. Earth-centric system is mostly used for Earth observation satellites, and heliocentric is mostly for other bodies around the solar system, asteroids, comets, other planets, spacecrafts, and so on and so forth. But there's also other concept about the time itself, right? You want to know where the position of a spacecraft is, and you want to know at what time it is, right? Like I told you, right? There's like a plane, and you throw it in a room, and you close your eyes, and you want to know in 5 seconds where it is. After 5 seconds, where is the spacecraft? This is what you want to know, and this is the time references. So we all know, or everyone on Earth uses a time, UTC time, right? We all know that we all use time. When you want to check your watch, you know the time, right? So the thing about that is not the only standard, or that is not the standard that normally everyone uses. This is not precise enough. right? Because the time that you use right now is based on how Earth is rotating, right? Let's say in simple terms, but this is not accurate because the position of Earth is changing, is always changing, and you have to periodically correct the time, right? And when this is also changing over time, it changes and so on and so forth. It's not accurate enough. We use the so-called TDB time. So what you have to know is that there's also more accurate standard. That is what everyone uses in any kind of calculation, right? So these are the basics of it. You know the position, and you have time references. There are also other things about you need to solve for 2-body and 3-body problems and so on and so forth. They're a little bit complicated. We don't need to talk about it. But the most interesting part is this is already done at the time of mission planning. Any scientist in, let's say, NASA or ISRO, for example, Aditya L1, right? We reached the Lagrange point, and it did not take so there were periodic corrections, if you remember, right? They initially planned something and then they found it not going accordingly, and there was some correction maneuvers, right? The same thing happened to Chandrayaan-3 orbit, Chandrayaan-3 propulsion module, right? ISRO did some crazy orbital mechanics, and then they got it back to Earth. You've seen, if folks who have seen my simulation would really know this, because the folks in ISRO are really awesome, because this kind of orbital mechanics is really very, very difficult to do. At least we have not seen anywhere. And I've talked to a lot of people, and then they said this is the mission that has been planned. It's very, very, let's say, ingenious, very, very cool. And also the one from SLIM. The most they chose the most economical path to reach the moon, right? And this is the most interesting part. I mean, this is the most chunk of the research that has to be done. There's a lot of research that has to be done. A lot of effort goes to this kind of planning, so you need to have extra respect for people who do this kind of things. I don't do this thing. I only watch the data, so I'm not into orbital mechanics. It's a way too complicated topic. But the interesting thing is this is already pre-calculated. We don't have to, as a normal Janta, we don't care about this. The background that I gave you is just to understand what you're looking at. So there are, if you're interested in looking at the planning software, there is an open source tool called as GMAT, also from NASA. General Mission Analyzing Software, something like that. I don't remember. That's called as GMAT. I think Scott Tilley uses GMAT all the time in his simulations. You could see it. So that's about mission planning. So this is a little bit background about what's out there, right? So this is what you so-called as a trajectory. So when you say trajectory, it means these ephemeris: position, velocity, attitude, and with some other details. Mostly these. But if you want to plot this, if you want to know the trajectory of something, you need to get it from somewhere, right? You need to know what kind of formats that these are there. So that's what I want to tell you. So any spacecraft, any satellite needs to know this ephemeris, needs to know their position data, right? When it's launched, it needs to know where it is. For example, for IM-1, as you've seen, it did not know its location. There was some problem with this with the instruments, and it wasn't able to adjust the position or something. There were some problems with it, and these are the onboard navigation systems. There are a plethora of sensors in the onboard navigation systems. There are sun trackers. There's a star tracker. There's gyroscope. There's magnetometer, and so on and so forth. All these sensors they act in unison. So together, with combining all the data from these sensors, the spacecraft know exactly where it is going, or where it will go, and it will know how fast it is going and which orientation it is. We'll talk about orientation a little bit later, but it will know about orientation about it, and then it will know if it has. So what's interesting is that there are bunch of instruments in the spacecraft, right? There's also communication instrument. There's also cameras. All these instruments have their own attitude. They have their own orientation. So all this information is already there in spacecraft, and they send this data. All this data is sent to the ground station, and these information is passed along to public by the space agencies as the so-called SPICE data, right? So this is what you need to have. You need to have some SPICE in your life. So SPICE is a format where this kind of information is passed on to the general public, to you and me and everyone. So the data, the details itself is not important right now. At least SPICE is called Spacecraft Planet Instrument T Matrix Events. Big long acronym. So SPICE data has a lot of details in it. It's maintained by NICE, also from NASA, and they define a format to distribute the data, and this data is so-called as a kernels, right? So the SPICE data has been distributed, right? So you have two data now. You have the raw ephemeris, position data, and you have SPICE data. So these are the two major formats to know about trajectories. These are the two major. SPICE is more detailed. It has more information about instruments as well. And ephemeris, they also know about the general information about how fast it is going, position and velocity, attitude about the spacecraft itself. Two different kinds of information. Both of these are available to public. Everyone can download it. So most of this data, for example, SPICE data, can be downloaded by space agencies. For example, for Chandrayaan-2, I've downloaded this data from ISRO Pradhan website. If you go to ISRO Pradhan, there is something called as SPICE there. If you click on it, you would find all this data. And these data are really, really precise, like really precise data. And for all the spacecraft, for example, for SLIM, Aditya L1, Chandrayaan-3, Astrobotic, IM-1, and also many more in the future, these are really current missions. These are all this data. For example, Astrobotic is a private company. It doesn't release this data at all. They are not obliged to release them. IM-1 doesn't release the data. But despite that, I did plot their trajectories. So how is this possible? Like, how would I know this? This is... again, with the courtesy of NASA JPL Horizon systems. There's a portal in NASA, basically. It's called JPL Horizons. There they release this data in their website. All of them. They release larger bodies information, ephemeris for large bodies, small bodies, and also special bodies for like asteroids, comets, and also special points like Lagrange point. I've used this data to plot for Aditya L1. All this information is available in the Horizon system. So this is the raw data, right? You have the data, and now look at the software. So how to use this? The majority of my simulations was done by Orbit Simulator. This is created by Tony Dunn. I think if you have noticed, if someone has noticed, this credits line in my simulations is done by Tony. So Tony wrote the simulation a long time ago, and it's a very simple simulation. It's a web app. It runs on the browser, and you could look into, you could just go to orbitsimulator.com, go there, and then you would find the simulator. It's a very simple website, but it's very versatile, and it supports lightweight scripting with JavaScript. So you could also tinker around it. And at the beginning, I got a lot of support from Tony. He even went and adapted the simulation. So if you have seen, in my simulation, during the re-entry of Astrobotic, I think I already found when Astrobotic, their Peregrine lander, was supposed to hit Earth, right? The atmospheric re-entry, when it would land, and at what place, and I found everything just based on the trajectory data. Right, the trajectory data doesn't give you that information, but you can get the information from the simulator. So this is the power of the simulator, right? You could use all this stuff just with time. and that's the first one I use. Most of my simulator are around this, and I need to thank Tony on this because he helped me a lot on the beginning, changed it, adapted it so that I'm able to write the simulators. So thanks to him. The other one is the so-called SPICE, Enhanced Cosmographia. This is the more realistic simulator. If you've seen my SLIM simulation, the whole 3D simulation, this is the software that I use, and this supports 3D geometry with CAD models. So essentially, what you could do is you have a CAD model of any spacecraft. You could import it into Cosmographia and then build your trajectories in it. It's a little bit more sophisticated. You could use Python to do more advanced scripting in it, and then you could write the trajectories of it. I think Slim is one that I used recently, and there's also a simulation that I will release tomorrow. This is I think I've done some teasers about it some time ago. It is the Chandrayaan 2 going and then taking a picture of Chandrayaan 3 lander. So this is precise movement when and how it went to Vikram lander and then took a picture of it. This is a little bit very, very cool simulation. I'm going to release it soon. But this is another simulation that you could use. So both are very interesting. Orbit Simulator is a little bit more simpler, and it supports JPL directly. So that's another added advantage. But a little bit, feature-wise, a little bit less feature. It's not realistic enough. But yeah, that's it. Cosmographia and Orbit Simulator, both are the most interesting in this space. And I think that's it. I mean, of course, there's a lot more information here, but I think it should be enough for this space. So.
Yeah, so really thank you for all the information which you shared. So come on, guys, now we want people from this XSpace to create simulation. Like, I believe Chandra would be happy to see more simulation from you guys too.
Yes,
so
I would like it.
Yeah. So also, like, if you are interested in learning orbit simulation, then we will soon roll out a Google form link. So like, do fill it if you are interested. So if like many people are interested, then we will request Chandra to start series on how to make orbit simulation. So like, stay tuned for it. Chandra, anything else that you want to mention about like series or like orbit simulation series?
Yeah, that's right. So this is what I'm planning. I think there's enough interest in. I think Path is also interested in this. So if there's enough interest, then I could start a series about the simulation itself. So I will explain you how to download the data. I mean, I'm going to go a little bit more detail into this concept that I spoke about, and then where to download it, and then how to convert this, and probably share some of my scripts to convert the data, and then make your own simulation and then use it. So you don't need to you don't need to wait for anyone. You can download the data. Data is available. Come to my space. We could do a little bit more interactive session on it, and then I can explain you how to create this cool simulation. Stay tuned for my simulation tomorrow.
Okay, so guys, like, we will also share the link of different simulation which Chandra has made. Like, we have shown 2-3 simulations by him on our YouTube live. So okay, thank you for joining, guys. So as we depart from our XSpace, let us carry with us the spark of curiosity, the flame of passion, and the determination to continue our exploration of the universe, both individually and collectively. For it is through our shared efforts and unwavering commitment to the discovery that we will continue to push the boundaries of human knowledge and boldly go where no one has gone before. Thank you all for being part of this incredible journey. Until we meet again under the boundless expanse of the cosmos, keep looking up, keep dreaming, and keep exploring. Thank you, guys. This is Zeta Gravit signing off. Thank you for joining once again. Thank you.